Swayam Prabha. Digital India. Educated India.
Very good morning to everyone. So, we will be looking into, if you remember whatever we have done in the last class, we have just looked into the theorems in the continuous domains, and the development will be basically our aim is in this portion of the syllabus is in order to solve the partial differential equations, and we will be looking into the only linear and homogeneous partial differential equations. In the last few classes, we have looked into how we can classify and categorize the partial differential equations into parabolic, elliptical and hyperbolic form. Not only that, we have also looked into the several boundary conditions those are associated in order to solve a partial differential equations, and we categorized different types of boundary conditions as well. Now, in this class what we will be looking into, we will be formulating the standard eigenvalue problem in continuous domain. Earlier we have looked into how these problems can be formulated in discrete domain whenever we talked about the matrices, and that eigenvalue eigenvector method was utilized in order to solve a system of algebraic equations or a system of ordinary differential equation. We will be developing the theory for the continuous domain in order to solve the partial differential equation. So, let us look into a particular form of equation. Consider the equation in the form d square y dx square plus lambda y is equal to 0. Let us consider a second order ordinary differential equation of this particular form subject to the boundary conditions at x is equal to 0, y is equal to 0, at x is equal to 1, y is equal to 0. So, therefore, we have selected a homogeneous equation with homogeneous boundary conditions. Okay. So, now clearly in this equation, since the equation and the governing equation and the boundary conditions are clearly satisfied by the solution y is equal to 0. So, therefore, y is equal to 0 is a solution to this problem but this solution is not a solution that we are looking for. This solution is known as a trivial solution. So, y is equal to 0 is of course a solution, but it is a trivial solution, and we are not looking for that. What we are looking for is that we are looking for non-trivial solution. So, we are basically looking for a solution, non-zero solution for different values of lambda. So, what are the values of lambda, so that this will be giving you a non-trivial solution. So, if that exists, if there exists a lambda, that is a scalar for which a non-trivial solution of y is obtained, then we call lambda as an eigenvalue. Of the system, corresponding y is or corresponding y or the solution is known as the eigenfunction. So, one has to be very clear that one can formulate an eigenvalue problem if and only if the boundary conditions are homogeneous. We can formulate an eigenvalue problem if and only if for a completely homogeneous system. What do you mean by the homogeneous system? By homogeneous system, we mean is that the differential equation is homogeneous, the boundary conditions are also homogeneous. If the differential equation and the boundary conditions both are homogeneous, then we call that system as homogeneous system. Now, for a completely homogeneous system, there exists an eigenvalue problem. So, eigenvalue problem means first we have to check whether the boundary conditions are homogeneous as well as the governing equations are homogeneous. Then only we call that problem an eigenvalue problem, and if the governing equation and the boundary conditions satisfy these two basic criteria or property, then we should go ahead for the solution of solution for the eigenvalues and corresponding eigenfunctions. Now, for this particular problem, let us solve this equation and see what are the eigenvalues we are getting and the corresponding eigenfunctions. So, we assume lambda, the constant lambda is real. If lambda is real, then there are three possible values lambda can assume. Number 1, lambda is equal to 0. So, that is possibility 1. Second part is lambda is negative, let us say it is minus alpha square. So, this simply indicates lambda is negative, and third is lambda positive. This simply indicates lambda is positive. So, let us consider these three cases separately and see what you get. First case will be lambda is equal to 0. If that is the case, let us see what is the form of our differential equation. Now, the differential equation boils down to d square y dx square is equal to 0, and because lambda itself is 0. So, we just integrate it and let us look into the solution of this. We integrate this out. If we integrate is this equation, the first integration results to dy dx is equal to some constant c1, and second integration leads to y as a function of x is equal to c1 x plus c2. Now, these two constants C1 and C2 should be evaluated from the two boundary conditions whatever we have. Let us write down the two boundary conditions. At x is equal to 0, y is equal to 0, that if we put this boundary condition here, let us see what we get. 0 is equal to C1 times 0 plus C2. So, therefore, C2 is equal to 0. If C2 is equal to 0, the form of the equation is has become now y is equal to C1x. Now, let us put the other boundary condition, that at x is equal to 1, y is equal to 0. So, if we utilize this boundary condition, let us see what we get. If we put x is equal to 1 into y is equal at y is equal to 0, if we look into the solution is y is equal to C1x, and at x is equal to 1, y is equal to 0 gives me an equation C1 times 1. So, that simply implies that C1 is equal to 0. So, what we get, if you look into a solution, you will be getting y C1 x plus C2, both C1 and C2 turns out to be 0. So, therefore, y is equal to 0 is the solution that we are getting. But this solution is a trivial solution. Therefore, one should not, so this trivial, we are not looking for a trivial solution, we are looking for a non-trivial solution. So, therefore, lambda cannot be is equal to 0. So, lambda is equal to 0 is ruled out. So, we cannot use that anymore. So, what is the, let us look into the second option. Second option is lambda is negative. So, lambda is equal to minus alpha square. So, lambda is negative. Now, let us see what is the form of our differential equation under this condition of lambda. Differential equation becomes d square y dx square minus alpha square y is equal to 0. So, if you know the solution form of this solution is e to the power m x. So, the form of the solution is in the form y is equal to e to the power m x is the form of solution. So, if we do that, we just put y is equal to e to the power m x, and what, let us see what you get. You will be getting a polynomial of order 2 of m, and that equation is known as the characteristic equation. So, if we put it that way, so dy dx, if y is e to the power m x, then dy dx is nothing but m e to the power m x. We differentiate it once more. So, it becomes d square y dx square is equal to m square e to the power m x. Now, we put all these value in the differential equation. Differential equation is d square y dx square minus alpha square y is equal to 0. If we put this here, m square e to the power m x minus alpha square y is e to the power m x. So, it will be e to the power m x is equal to 0. Now, m being not equal to 0. So, e to the power m x is always positive. So, m square minus alpha square is the solution. So, m will be having a solution plus minus alpha. So, therefore, the form of the solution will be in this form. So, this is known as the characteristic equation. So, form of the equation will be, solution will be C1 e to the power alpha x plus C2 e to the power minus alpha x. So, m will be having two roots m1 and m2. So, form of the solution will be C1 e to the power m1 x plus C2 e to the power m2 x. In m1 we put plus alpha, in M2 we put minus alpha. So, now with this solution we put the boundary conditions. So, let us write form of the solution as C1 e to the power alpha x plus C2 e to the power minus alpha x. Next, we write down the boundary conditions at x is equal to 0, y is equal to 0, at x is equal to 1, y is equal to 0, the homogeneous boundary conditions. Now, if you utilize the first boundary conditions, let us see what we get. We will be getting 0 is equal to C1 e to the power 0 is 1 plus C2. So, C1 is equal to minus C2. So, the solution is we put C1 is minus C2. So, minus C2 e to the power alpha x plus C2 e to the power minus alpha x. So, minus C2 you can take it common. So, e to the power alpha x minus e to the power minus alpha x. Now, we put the other boundary condition and see what is the fate of y of the constant C2. So, one constant has to be, this constant has to be evaluated and one boundary condition is left. So, you will be having 0 minus C2 e to the power 1 minus e to the power minus e to the power alpha minus e to the power minus alpha. Now, if you remember the variation of e to the power alpha as a function of alpha, it will be for alpha is equal to 0, we have ruled out alpha is equal to 0, because if alpha is equal to 0, we are going to get a trivial solution. So, for even for alpha is equal to 0, e to the power alpha is 1, from 1 onwards for any positive value of alpha, it will be ever increasing function, it will be always positive. Similarly, if you look into the so this is the variation of e to the power alpha. I am plotting the variation of e to the power alpha and e to the power minus alpha as a function of alpha. So, e to the power alpha is always positive, the minimum value is 1 and the maximum value will be always positive, and the higher values will be always positive. If you look into the value of e to the power minus alpha, for alpha is equal to 0, e to the power minus alpha is 1 and it decreases exponentially. For e to the power minus alpha minus infinity, it will be 0, but so it varies from 1 to 0. So, therefore, e to the power minus alpha is always positive. So, what I mean by this analysis is that e to the power alpha is ever positive, e to the power minus alpha is always positive. So, their combination is always a positive quantity. So, in order to satisfy this equation, only option is that C2 is equal to 0. Now, if C2 is equal to 0, from this we will be getting C1 is equal to 0. So, what is the fate of my solution? The fate of my solution is 0 multiplied by e to the power alpha x plus C2 is 0 multiplied by e to the power minus alpha x. So, the full solution becomes 0. So, again we are landing up with a trivial solution. So, this is nothing but a trivial solution, and we are not looking for a trivial solution, we are looking for a non-trivial solution. So, therefore, therefore, lambda cannot be a negative quantity, is not possible. So, lambda is minus alpha is also not possible. So, we have, if you remember, we have 3 choices for real value of lambda. Lambda is 0, that is ruled out because we are getting a trivial solution. Then lambda is negative, that is also ruled out. So, because we are getting a trivial solution. So, only option that we are leaving with is only lambda is positive. And let us see what do we get. Case number 3, lambda is positive and it is equal to plus alpha square. So, d square y dx square plus alpha square y is equal to 0. So, let us again look into the solution. The form of the solution is again y is equal to e to the power m x. So, we just put the double differentiation of this equation here. So, this becomes m square e to the power m x plus alpha square e to the power m x is equal to 0. So, what we get is m square plus alpha square e to the power m x is equal to 0, and e to the power m x for non-zero value of m and x, it will be ever positive. So, m square is equal to minus alpha square. So, what we get is that what is the solution? The solution is of course minus e root over plus minus root over e to the power minus alpha square. So, it will be root over minus 1, it will be nothing but I, imaginary quantity. So, it will be plus minus I alpha. So, that is the solution of this characteristic equation, and the two roots are I alpha and minus I alpha. So, let us see how the solution of the differential equation is now takes the form. So, y is equal to, as a function of x, this is equal to c 1 e to the power m 1 x plus c 2 e to the power m 2 x. So, the form of the solution is c 1 e to the power I alpha x plus c 2 e to the power minus I alpha x, and if you know, you can write the Euler's equation, thus e to the power I alpha is nothing but cosine alpha plus I sin alpha. Now, if you write and e to the power minus I alpha is nothing but cosine alpha minus I sin alpha. If you open up these two quantities and write it down in this equation, finally, you will be getting the solution in the form of periodic functions. These cosine and sine functions are periodic functions, and it will be combination of the sine function and the cosine function. So, final form of the solution becomes C 1 sin alpha x plus C 2 cosine alpha x. This imaginary quantity i's etcetera will be consumed in the constants C 1 and C 2. So, now let us put the boundary conditions at x is equal to 0, y is equal to 0. So, let us see at x is equal to y equal to 0. So, put y is equal to 0, then C 1 sin 0 plus C 2 cosine 0. Now, sin 0 is always 0, cos 0 is 1. So, 0 is equal to so 0 multiplied by C 1 is 0. So, this will be 1. So, C 2 is equal to 0. So, this boundary condition gives me the solution as C 2 is equal to 0. So, what is the solution of y x? It is nothing but C 1 sin alpha x. Okay. Now, let us put the other boundary condition and see what we get as the solution of this equation. Other boundary condition is at x is equal to 1, y is equal to 0. So, if you put y is equal to 0, C 1 sin alpha. Now, there are two options of getting the solution, either C 1 is equal to 0 or sin alpha is equal to 0. If we use C 1 is equal to 0, then again we are going to land up with a trivial solution. So, if C 1 is equal to 0, we get a trivial solution. So, that is ruled out. So, we are not looking for a trivial solution, we are looking for a non-trivial solution. Therefore, C 1 cannot be is equal to 0. So, what is the option left? The option is left as sin alpha is equal to 0. If you look into the solution, generic solution of sin alpha is that the alpha of this solution of this equation is alpha n is equal to n pi, where your n's are varying from 1 to 3 up to infinity. Now, n is equal to 0 is ruled out, because if we put n is equal to 0, then alpha will be equal to 0. If alpha is equal to 0, then again we are going to get a trivial solution. So, for getting a non-trivial solution, the solution is alpha n is equal to n pi, where the index n runs from 1 to infinity. Now, for each value of n, the corresponding value of alpha are known as the eigenvalues. So, this is nth eigenvalue of the system, and what is the corresponding eigenfunction. We denote the so what is, if you look into the solution, what is the solution? The solution was C1 sin alpha x. So, corresponding to nth eigenvalue, we will be getting the nth eigenfunction. We denote it as y subscript n. So, this becomes C1 sin alpha n. So, this becomes alpha n x, and alpha n become n pi. So, it becomes n pi x. So, this is the nth eigenfunction. So, we get the corresponding eigenfunction is sin n pi x, and corresponding eigenvalue is n pi. So, next what we will do, we just change the boundary condition from Dirichlet boundary conditions. So, what we have? We have the boundary conditions, homogeneous boundary conditions are at x is equal to 0, y is equal to 0, and x is equal to 1, y is equal to 0. These are the Dirichlet boundary conditions. Now, let us see what is the form of eigenvalues and eigenfunctions in case of a Neumann boundary condition. So, again we look into the problem in a different way by changing the boundary condition. The form of the equation remains same, d square y dx square is equal to plus lambda y is equal to 0. Now, what we do? We change the boundary condition, one boundary conditions from Dirichlet to Neumann. So, subject to at x is equal to 0, we have a boundary condition dy dx is equal to 0, and at x is equal to 1, we have y is equal to 0. So, what is the difference between this problem and earlier problem? The governing equation remains the same, only the Dirichlet boundary condition at x is equal to 0 is replaced by a Neumann boundary condition dy dx is equal to 0, and the other end at x is equal to 1, the boundary condition remains the same, it is a Dirichlet boundary condition. So, that is the difference between this problem and other problem. So, it is a but you please remember, notice that the ordinary differential equation and the boundary conditions both are homogeneous, only the nature of boundary condition has been changed at the surface or at the boundary x is equal to 0. So, we note this down, both differential equation and boundary conditions, they are homogeneous. Only the boundary condition has been changed. So, again there will be we solve these three cases, this case completely. So, there will be three options for real alpha. For real values of alpha, there will be three cases. Case 1, alpha is equal to 0. Case 2, alpha is negative. So, let us say that was lambda, right. So, this one was lambda. So, we put lambda is equal to 0. lambda is minus alpha square. So, lambda is negative, and the third option is lambda is equal to plus alpha square. So, it is positive. Now, we examine all these three cases one after another. So, case 1 will be lambda equal to 0. So, what we will be getting is that d square y dx square is equal to 0. Now, we have already seen earlier the solution of this equation is y is equal to c 1 x plus c 2. Next, we put the boundary conditions, utilize these two boundary condition and evaluate the constants c 1 and c 2 and see what we get. Now, if we really do that, what we will be getting is that solution is c 1 x plus c 2 at x is equal to 0, dy dx is equal to 0. So, if we evaluate dy dx of this equation, what we get is dy dx is nothing but c 1. So, at x is equal to 0, dy dx is equal to 0, use that boundary condition. So, what you get is c 1 is equal to 0. So, therefore, the solution is c 1 is equal to 0. So, you will be getting y is equal to c 2. So, therefore, the solution is a constant solution. Now, use the other boundary condition, that is at x is equal to 1, y is equal to 0. So, there is no variation of x with respect to y. Since y is constant, in order to satisfy this boundary condition, then you have to have y is equal to 0, c 2 is equal to c 2. So, if you remember that whatever I have told in the last class, that differential equation must be valid throughout the whole boundary as well as throughout the whole control volume, as well as it is valid only at the also on the boundaries, but the boundary conditions are valid only at the boundaries. So, let us note down this point and use it. So, differential equation is valid at any point inside the control volume as well as on the boundary. On the other hand, the boundary condition are valid only at boundaries. They need not to they should not they need not to valid within the control volume. So, therefore, my differential equation must be satisfying every point inside the control volume as well as it must be satisfying the boundary condition. Now, if we have seen that solution of the differential equation is a constant, that constant is equal to c 2, but the differential equation must be equal to 0 at the boundary x is equal to 1. So, these two can go hand in hand if and only if we put y is equal to 0 is equal to c 2. So, therefore, c 2 becomes 0, and if you look into the solution, c 1 is 0, c 2 is 0. So, you will be getting y is equal to 0 is a solution. And if you remember, this is a trivial solution. So, what is our conclusion? Our conclusion is that alpha lambda cannot be negative. Lambda cannot be minus alpha square. So, that is ruled out. So, what we have done till now? We have ruled out that lambda cannot be is equal to 0, lambda cannot be is equal to minus alpha square, because both of these leads to only trivial solution. and we are looking into the non-trivial solutions. So, the third option is now left, the lambda is positive and it is equal to plus alpha square. Okay, so let us again look into the solution, d square y dx square plus lambda y is equal to 0. So, put lambda is equal to alpha square. So, you will be getting d square y dx square plus alpha square y is equal to 0. So, again e to the power m x is the form of the solution and we have already solved this equation earlier. I am not going to solve this equation once again here. So, if you look into the characteristic equation, the characteristic equation will be in the form of m square plus alpha square is equal to 0. So, you will be having two roots, m 1 2 is nothing but plus minus I alpha. So, therefore, the solution will be composed of sine functions and cosine functions, periodic functions. So, y is equal to y as a function of x becomes c1 sine alpha x plus c2 cosine alpha x. That is the form of the solution, and let us put the boundary conditions and evaluate c1 and c2. The first boundary is y is equal at x is equal to 0 dy dx is equal to 0. So, if we put this boundary condition and let us see what is our solution, y as a function of x is nothing but c1 sin alpha x plus c2 cosine alpha x. Now, we evaluate dy dx, dy dx becomes c1 alpha cos alpha x minus c2 alpha sin alpha x. Remembering that differentiation of sin alpha x is nothing but alpha cosine alpha x and differentiation of cosine alpha x nothing but minus alpha sin alpha x. Now, putting x is equal to 0, dy dx is equal to 0, what you will be getting is 0 is equal to c1 alpha cos 0 is 1 minus c2 alpha 0. So, you will be getting c1 times alpha is equal to 0, alpha is not equal to 0, because if alpha is equal to 0, you will be landing with a trivial solution again, and we are not looking for a trivial solution. That means, c1 is equal to 0. If c1 is equal to 0, let us see what we get. So, as a solution. So, solution we will be getting is y as a function of x, since c1 equal to 0. So, we will be getting c2 cosine alpha x. So, that is the form of the solution we are getting, and this solution is a non-trivial solution. Now, we have to check, we have to evaluate the eigenvalues and eigenfunctions. So, we have one more condition that is left behind, that is the boundary condition at x is equal to 1. So, at x is equal to 1, we have a Dirichlet boundary condition there. So, we put y is equal to y x as 0 and this becomes c2 cosine alpha, we put x is equal to alpha. Again, in this equation c2 cannot be equal to 0. Why? If c2 is equal to 0, again we are going back to a trivial solution and we are not looking for a trivial solution. So, what is the option left? The option left is cosine alpha is equal to 0 for a non-trivial solution. If cosine alpha is equal to 0, then let us look into what is the general solution for this equation. We have already we all studied the general solution of sin alpha equal to 0, cosine alpha is equal to 0 in our 10+2 standard. So, the general form of this equation is alpha n is 2n minus 1 pi by 2. where the index n runs from 1 to up to infinity. So, this is the general form of the solution. Now, each of these values of alpha for which cosine alpha is equal to 0 is the eigenvalues for this particular problem. So, alpha n is equal to 2n minus 1 pi by 2 is the nth eigenvalue of this problem, and the corresponding solution is the nth eigen function. So, y n as a function of x is nothing but this is nth eigen function, and this becomes cosine alpha n x. So, therefore, this becomes cosine 2n minus 1 pi by 2 into x. So, alpha n is equal to 2n minus 1 pi by 2 is the nth eigenvalue, and y n cosine 2n minus 1 pi by 2 times x is the nth eigen function. So, this is the eigenvalue, this is the eigen function. So, if you look into the solution for this particular problem, by changing the boundary condition from Dirichlet to Neumann, we land up with a different eigenvalue and eigen function combination. Next, what we do, we will change the boundary condition to the third kind of boundary, which are quite common in chemical engineering applications, that is a Robin mixed boundary condition. So, we change the boundary condition, we keep one boundary condition Dirichlet, and like this particular case we change the boundary condition to of the other boundary condition to Robin mixed boundary condition, and see what are the eigenvalues and eigen functions we are getting in this case. So, let us consider the same equation d square y dx square plus lambda y is equal to 0, but we change the boundary conditions in this case subject to B c at x is equal to 0, y is equal to 0. We keep the Dirichlet boundary condition here as it is, we change the other boundary condition at x is equal to 1, we use a Neumann, we use a Robin mixed boundary condition. So, that will be dy dx plus beta y is equal to 0. Please check that again we have a homogeneous system of equation, the differential equation and boundary conditions are all homogeneous. What we simply did, we keep this Dirichlet boundary condition as it is, we change the boundary condition to the other boundary condition, that is at x equal to 1, we made it a Robin mixed boundary condition where beta is a constant. So, therefore, what we get is that we look into the again this lambda can be for real values of lambda. It can be three things, lambda can be 0, lambda can be negative, and third option is lambda is positive. Let us examine all the three cases in detail and see what kind of eigenvalues and what kind of eigen functions we are getting in this particular case. So, for lambda, so case 1 is lambda is equal to 0, and again the form of differential equation is d square y dx square is equal to 0, and we know the solution to this problem, and the solution becomes y is equal to c 1 x plus C2. Now, let us put the boundary conditions. The first boundary condition is at x is equal to 0, y is equal to 0. If you put that, you will be getting y is equal to C1 into 0. So, it will be 0 y. So, y is equal to 0 is equal to C2. So, C2 will be equal to 0. So, what is the solution? The solution is y is equal to C1 x. Now, if we use the other boundary condition, that is at x is equal to 0, dy dx plus beta y is equal to 0. So, we put at x is equal to 0, dy dx, what dy dx is C1, and we put this here. So, C1 at x is equal to 1, sorry, at x is equal to 1, dy dx plus beta y is equal to 0, that is the other boundary condition. So, it is boundary condition is defined on two boundaries at x is equal to 0 and x is equal to 1. So, this becomes dy dx is C1 plus beta times y. So, beta times y evaluated at x is equal to 1. So, this will be beta C1 times 1 should be is equal to 0. So, C1 into 1 plus beta is equal to 0. Now, beta is a constant, it is a positive constant. So, therefore, 1 plus beta is always positive. So, 1 plus beta always positive, it cannot be equal to 0. So, beta can be positive or it can be negative. So, therefore, 1 plus beta is not equal to 0. So, in order to satisfy this equation, C1 must be equal to 0. So, if C1 is equal to 0, so what is the form of our solution? This is the solution we had. So, y is equal to C1 is 0. So, y is equal to 0. So, y is equal to 0 we are getting as a final solution for this case as well. So, this is giving a trivial solution. And we are not looking for a trivial solution. So, therefore, lambda cannot be equal to 0 in order to get a non-trivial solution. So, in order to get a non-trivial solution, lambda is not equal to 0. So, what is the next option? The next option is lambda is negative, and see what we get. So, case 2, lambda is minus alpha square and it is negative. So, our differential equation now becomes d square y dx square minus alpha square y is equal to 0. If you remember, the form of the solution to this equation is e to the power m x, and m square is equal to minus alpha square is the characteristic equation. So, the solution will be composed of e to the power y is equal to e to the power alpha x plus C 2 e to the power minus alpha x. Now, let us put the first boundary condition. The first boundary condition is at x is equal to 0, you have y is equal to 0. So, therefore, this will be 0 C1 plus C2. So, C1 e to the power 0 is 1 and e to the power minus 0 is also 1. So, it will be C1 plus C2. So, therefore, we will be getting C2 is equal to minus C1. So, the form of the solution becomes y as a function of x. So, C1 C2 is equal to minus C1. So, take C1 common, e to the power alpha x minus e to the power minus alpha x. Okay. So, next what we do? We utilize the other boundary condition. The other boundary condition is at x is equal to 1, we have dy dx plus beta y is equal to 0. So, let us evaluate. So, if we look into the solution is y as a function of x is c 1 e to the power alpha x minus e to the power minus alpha x. So, we evaluate dy dx and see what we get. Dy dx is c 1 alpha e to the power alpha x minus plus alpha e to the power minus alpha x. So, we can take alpha common. So, c 1 alpha e to the power alpha x plus e to the power minus alpha x. Now, we put the boundary condition at x is equal to 1. So, dy dx will be evaluated at x is equal to 1 e to the power alpha x plus e to the power minus alpha x. The whole term is evaluated at x is equal to 1 plus beta times y is c 1 e to the power alpha x minus e to the power minus alpha x, whole term evaluated at x is equal to 1 should be is equal to 0. So, we evaluate that. So, this becomes c 1 alpha e to the power alpha plus e to the power minus alpha plus beta times c 1 e to the power alpha minus e to the power minus alpha is equal to 0. So, we can take c 1 common. So, this becomes alpha e to the power alpha plus e to the power minus alpha plus beta e to the power alpha minus e to the power minus alpha is equal to 0. Now, as we have argued earlier that if we have looked into the variation of e to the power alpha and e to the power minus alpha with respect to alpha, this is the variation of e to the power alpha and that is the variation of e to the power minus alpha. So, therefore, e to the power alpha is always positive having a minimum value 1, e to the power minus alpha is always positive with a maximum value as 1. So, their combination is positive, again their combination is positive, beta is not equal to 0. The whole thing in the third bracket is a positive quantity, that means. So, in order to satisfy this equation, we have to have c 1 is equal to 0 and let us see what if c 1 is equal to 0. If we look into the solution, the solution was y is equal to c 1 e to the power alpha x minus e to the power minus alpha x. For c 1 is equal to 0, of course, you will be getting y is equal to 0, which is nothing but a trivial solution. So, therefore, we are going to get a trivial solution in this case as well. So, our conclusion is our lambda cannot be a negative quantity, because it gives a trivial solution and we are looking for a non-trivial solution. So, I stop here at in this class at this point. I will take this point on in the next class and we will be completing this problem in the next class, and then we will take a stock of what are the forms of eigenvalues and eigenfunctions if we change the boundary conditions slightly. Thank you very much.